Hi students, Professor Nugent here. In this video, we continue yet again our discussion on the F distribution. Your regression printouts might refer to the F distribution. In fact, they almost always refer to the F distribution. Note that if the four multiple regression least square assumptions hold, and if the regression residual is homoscedastic, that is, the variance of the OLS residual conditional on x1 through xk does not depend on the x's, and all of the OLS and the OLS residuals for observations I through n are normally distributed, then the homoscedasticity only F-statistic has the FQ n minus k minus 1 distribution, where q is the number of restrictions, k is the number of regressors under the alternative, n is the sample size. Now, the F distribution is to the chi-squared over q distribution what the t n minus 1 distribution is to the standard normal distribution. So we're looking at, in essence, a distribution that asymptotically approaches the chi-squared over q distribution. The FQ, n minus k minus 1 distribution is different from the chi-squared over q distribution when the sample size is small. But when the sample size is large, then the F distribution is basically the same or exactly the same as the chi-squared over q distribution. You can find the F distribution tabulated in many places. For instance, try the Google. You'll see that as n approaches infinity, as we have just discussed, the F distribution asymptotes the chi-squared over q distribution. Hence, the FQ, infinity distribution and chi-squared over q distributions are the same. For q not too big and sample size greater than 100, these two distributions are essentially identical. Okay, so again, if you're not testing too many constraints in your null hypothesis and your sample size is at least 100, then the F distribution and the chi-squared over q distribution are essentially the same, and you're going to draw your critical values from the chi-squared over q distribution. Many regression packages, including Stata, compute p-values of F-statistics using the F distribution, and so we're going to encounter this in the work that you're doing for this course, and you will encounter the F distribution in published empirical work. And note that typically, almost always, we're going to be working with critical values from the chi-squared over q distribution, and we're going to be working with the heteroscedasticity robust F statistics. Here is a look at the F distribution for different degrees of freedom where the sample size is infinity. Okay, so look up here, we have critical values for the Fm, infinity distribution. So here we have assumed that the sample size is very large, and we have different degrees of freedom for the different number of constraints imposed in the hypothesis from 1 to 30, and the significance level at 10%, 5%, and 1%. These are essentially the 90th, 95th, and 99th percentiles of the F distribution, which are which serve as the critical values for tests with significant levels of 10%, 5%, and 1%. Alright, folks. So these are our critical values. I will note that we've been working with a 5% critical value, where we have one restriction, that 3.84. That should look familiar. Let's think about briefly the history of this distribution. The theory of homoscedasticity only, F-statistic, and the F distributions rests on implausibly strong assumptions, like whether financial data is normally distributed. These statistics date to the early 20th century, the days when datasets were small and computers were people. The F-statistic and F-Q(n-k-1) distribution were major breakthroughs. An easily computed formula, a single set of tables that could be published once, then applied in many settings, and a precise, mathematically elegant justification. These strong assumptions were a minor price for this breakthrough. The assumptions of, for instance, homoscedasticity. But with modern computers and large samples, we can use the heteroscedasticity robust F-statistic and the F-Q infinity distribution, which only requires the 4 least squares assumptions. It does not require homoscedasticity in the OLS residual, and does not require that the OLS residuals are normally distributed. This historical legacy of the homoscedasticity only standard errors and F-statistics persists in modern softwares and can be the default. And in this case, the p-values may be computed using the F-Q(n-k-1) distribution. These statistics are justified only under very strong conditions, which are stronger than realistic in practice, because in practice we often have heteroscedasticity, right? It is rare that we see homoscedasticity. You should use the heteroscedasticity robust F-statistic with critical values from the chi-squared/q distribution, which is the F-Q infinity distribution. These are the critical values that we want. For large sample sizes, the F distribution is essentially the same as the chi-squared/q distribution. Now, for small sample sizes, some researchers will use the F distribution with Q(n-k-1) degrees of freedom because it has larger critical values, and in this sense it is more conservative. You're setting a further benchmark, making it a little bit harder to reject the null hypothesis in that case. And if you can prove that setting a further benchmark you still reject the null hypothesis, then even in those conservative conditions you have proven your result to be robust. So let's sum up this F-statistic discussion on testing joint hypotheses. The one-at-a-time approach of rejecting if either of the t-statistics exceeds 1.96 rejects more than 5% of the time under the null does not work because the size of this test exceeds the desired significance level. We have shown that in this case the size of the test is actually closer to 10% when we want a level of significance about 5%. The heteroscedasticity robust F-statistic is built into Stata. This is the test command that you all now know, and this tests all Q restrictions at once, so it's very easy to implement. You just write test and then all those variables, and we will discuss later in class not only how to test restrictions that the coefficients are equal to 0, but other kinds of restrictions. The homoscedasticity only F statistic is important historically, thus in practice, and can help intuition, but will not be valid where there is heteroscedasticity. You will end up with a larger F statistic than is true, right? Than is true, and that's what we saw with the example with the test score data. And this sums up our discussion on the F statistic.